Good morning, everyone. Thanks for joining. Brandon said, my name is Alexis. It is my absolute pleasure to be introducing our third round of technical talks for this symposium with this morning session focused on networks, microelectronics, and hypersonics. We have 4 presentations for you in this morning session, which will last roughly an hour. If you have questions for our presenters, please do pop them into the chat. If we have time at the end of each presentation, we will pose those to our presenters, or they will have the opportunity to answer in the chat. Or if you think of something later that you want to ask one of our presenters, you can move it over to our Whova platform. So let's go ahead and get started for this morning. We will begin with Sean Mulcahy. Sean is with the Marine Corps Tactical System Support Activity out at Camp Pendleton, California. His project title is Accelerated Solution Development. So take it away, Sean.
Thank you, Alexis. Perfect. My name is Sean Mulcahy, and I am from Phase 2 Scholar, graduated or got the scholarship in 2017 with a bachelor's and master's combination funded. I got my computer engineering degree and a computer science degree from Michigan State University. And as stated, I work at the Marine Corps Tactical System Support Activity, or MCTSSA for short. I'm located in Camp Pendleton, California, which is about an hour north of San Diego. So what does MCTSSA do? So here's kind of our mission statement. In the blue is what we do. Green is who we do it for, and the yellow is why we do it. But to kind of summarize that into a single few word sentence, we really just test all the C4I systems or the communication systems that the Marines use to make sure they do what they're supposed to do. But if you want to simplify that even further, when you think of MCTSSA, just think of our job is to make Marines more capable. And I'm sure you've noticed by now the beautiful facility located a couple hundred feet off of the beach in Camp Pendleton. So for those potential scholars that want to have a beachfront office, consider looking to MCTSSA for your potential sponsored facility. But how do I fit into that mission that I just stated on the page before? So I kind of have 2 different hats at MCTSSA. I work as a developer in the Advanced Concept Cell, in addition to being kind of the STEM outreach lead at MCTSSA. And I'll explain what both of those are in a minute. So as the developer, this idea of accelerated solution development comes into play. So we, in the Advanced Concept Cell, develop tools for the engineers and testers that support the mission that I explained on the slide before. So we try to modernize their processes by incorporating automation, AI, better use of data, and things like that. And we do all that using Scrum and Agile methodologies, which plays a part in why we are so accelerated in our development. And then in regards to STEM outreach, I lead a team that does a lot of the recruitment and mentorship of the interns that we bring on from multiple programs, SMART being one of those. We sponsor collegiate teams, whether it be a capstone project or extracurriculars. And then finally, we do a lot of K through 12 outreach through hosting STEM days, STEM weeks, or just visiting the school to encourage the new generation to take on STEM. So accelerated. So when I say accelerated, I mean from the concept of an idea to a deliverable, actionable, or a usable product. We do that all in 6 months. So that's fast for the DoD from what I'm aware of. And that's all possible because we use Agile and Scrum. And for those not familiar with what Agile and Scrum are, this picture does a good job at kind of breaking down what that is. So you take your 6-month time frame, you then break it into smaller time chunks. For us, it is 2 weeks, and that's called a sprint. And then during that sprint, you do constant iterations on your product, meeting with the customer, defining deliverables, building those deliverables, and then giving that back to the customer. And this, by breaking it down, it really assists in the process of developing fast solutions because, as you can see on the bullets on the left, the benefits of Scrum with those self-imposed deadlines, the customer gets to see the product as it's being built rather than waiting 6 months to hand them something that might not even solve their problem. It also sets designated points for communication with the customer. So at the end of each sprint, the customer has an opportunity to voice their concerns over the product, which in the end, develops the relevant solution for our customers. So the solutions. So here's a list of some of the solutions that we have developed. There's many more, but these are kind of the three most popular ones that we have developed so far. So our analytic reporting system, or MARS, is used in collaboration with our network engineers. So our network engineers have these large PCAP files or packet capture files that measure the traffic between a few servers. And this tool would take those PCAP files, which could be gigabytes or terabytes, and it would then allow that to be ingested into our system. And then at the click of a button, the network engineer could generate a report based on whatever analytic they want to measure, whatever specific time range, or whatever thing they need for their final report. And that ultimately took their analysis down from weeks of work to days, or possibly even hours, depending how much data it was. Next project I want to mention is our Sparta Leo plus Leo project, which was done in collaboration with our cybersecurity team. So a penetration tester has an IP that they want to target with their system. So they would plug that IP into Sparta, and Sparta would automatically run scans against it, find out what version, what software is running on it, what version it is, and based off that information, it would run the most optimal scripts against that the penetration tester would store in a database. And this would enable the penetration tester to run hundreds of scripts at the click of a button without having to do much observing of what was going on in the back end. The final example is this employee portal that we were able to generate, which kind of gives some business insights into how we run tests at MCTSSA. So this tool would enable the employee to easily see and reserve resources for their test event, whether it be assets, personnel, lab spaces, or just measure what requirements they're going to test in their test event. And this not only helped them plan, but on the back end, delivered business insights to help leadership identify gaps in resources, where to invest in more roles or buy more radios, or whatever the case may be. And then development. So all these tools had different use cases, and as much as I love Python, I wish I could use Python to solve all of them, but the way that Advanced Concept Cell works is we're encouraged to explore and use open source technologies to really get a head start and not start from scratch every time. So here's just a quick picture of a lot of technologies we have used. And yes. So why does all this matter? This is it's kind of hard to get motivated since you're building these automation products that don't directly support the warfighter. But if you think of it kind of like a domino set, my team works as one of the first few dominoes that will eventually lead to supporting the warfighter. So if we build successful tools that help automate the processes of our teammates will then be able to perform their tasks better. If they perform their tests better, the test as a whole is performed better. Those tests will then lead to fielding decisions that be more efficient and happen quickly. And ideally, with better fielding decisions, the warfighter gets equipped with the best equipment faster. And then just to kind of take a step back from all that, SMART has had a large impact on how I have molded my career thus far. A lot of the scholars yesterday talked about with SMART in phase one, you get the opportunity to focus on school without the burdens of worrying about financial stability and whatnot. So I won't belabor that point too much, but the second 2 points have to do with the uniqueness of SMART, where you have that summer internship before you actually work at your facility, which is a unique experience because this internship is essentially an extension of your job. You get to try out and learn about the people, your future teammates, establish relationships, but also it gives you an opportunity to establish and learn skill gaps that your facility either has, or skill gaps or required skills that your facility needs that you currently don't possess. So during that summer internship, you can learn those gaps and then tailor your research or your coursework to fill those gaps. And then in phase two, this may be unique to MCTSSA or the Marine Corps, but The AC2 really exposes you to a startup-like environment. And by that, I mean, in many industries, you're kind of given code to retrofit or to modify to fix some problem that a previous developer made. In regards to my work in the AC2, we get to start from ground zero every time. We got to work directly with the customers to find requirements, go through different iterations, make failures, make successes. We go through all of that. But with the comfort of knowing that if the product isn't adopted or if the solution can't be found, we're not going to lose our jobs because we're encouraged to seek further innovation. Something else that I've not seen mentioned yet is you have access to extremely talented Marines or officers or warfighters. And when I say access to, like, their coding, we're pushing the same repositories. It's a very unique experience that you won't be able to experience anywhere else in the DoD, or not in the DoD, but in the industry. It's great because they have great stories and great intelligence and great insight into the problems that you're trying to solve. And then, particularly at my facilities, do a great job at driving the why. Why are we doing this work? So we schedule many field trips to different sites around Camp Pendleton or in Southern California, such as ship tours, or I've seen a few live fires, artillery, to see the different softwares communicating with each other, amphibious vehicle testing in the ocean, and stuff like that, which is a really cool experience, which might not directly help me code, but it really drives the why am I doing what I'm doing. And then one final note is I think SMART really set me up for success on this path. And I recently graduated from the Defense Civilian Emerging Leadership Program, which I highly recommend to all the Phase 2 and Phase 3 scholars if you're not aware of it. It definitely is the next progression out of SMART as you're trying to grow your career as a leader. And with that, I yield the rest of my time.
Awesome. Thanks so much, Sean. And thanks for, actually, we do have a question here from Dr. Kokenhauer and Dr. Ligon, so that's great. I'll get to those questions in a minute. I just wanted to highlight how important it is, and I'm glad that you distinguished between what work as a computer scientist, computer engineer within the DoD versus industry is like. It's one of our largest STEM fields, and it's definitely a challenge. I know I've talked with MCTSSA before numerous times, but just the real difference between the quality and level of work that you're able to do within DoD versus your partners in industry, and why that's more rewarding and more fulfilling than perhaps some of your friends and cohorts that went into private industry, and the difference between that. Okay, so we've got a question here. What is it like to code alongside Marines? Is that a unique experience, and what things have they taught you?
So coding alongside Marines, so usually the way it works, I'm usually working with officers because the enlisted usually come right out of high school, and they don't have that foundation that a lot of the officers have. But coding with them, specifically Marines, they have this stereotype of not being, just being all gunfighters, and they don't like technology or whatever the case may be. But working alongside these Marines really it motivates me more to get a product that works for them. As I develop things, they really tailor or give insight into the experience of the person that's going to be using the tool. And it's just, the knowledge transfer is also just, it's amazing. I just highly recommend being a computer scientist in the DoD for that experience alone.
Awesome. Yeah. And real quick, one more question about the Agile Scrum method. It looks very effective for completing your projects. Do you use that in the employee portal to track the team's progress? And is that portal or the tracking method you use available for other agencies?
So the employee portal was developed on a tool called Power Apps. It's a Microsoft tool. So I think the Marine Corps is kind of testing out the feasibility of that. But if another agency was to have access to Power Apps, I could easily give you access to it. It's just a pickup, and I can drop it off in your environment. What was the first part of that question again?
Just how effective Agile and Scrum is, and do you use it to track the team's progress? So we do not use the employee portal to track team progress. We have the other like Scrum boards using things like DI2E or Jira and all that type of stuff. But
ideally in the future that those two would be integrated to a single interface.
Great. Thanks so much, Sean. As other questions come in, Sean, feel free to answer those in the chat. Just a little plug from our outreach team. We're very excited to connect with you on the type of outreach that you're doing within your organization in STEM. So please do reach out to us and we'll reach out to you. So thanks so much for that.
Thank you.
All right, next we're going to move on to Dr. Neil Moser. Dr. Moser is with the Air Force Research Laboratory Sensors Directorate at Wright-Patterson Air Force Base in Ohio, and his project title is Active Load Pole Testing of Gallium Oxide Power Transistors.
Okay, can you see the slides or not?
Yes, perfect.
Okay. I cannot see myself though. Okay. I'll just go ahead anyway. So I'm Neil Moser. The presentation that I have here is called Active Load Pole Testing of Gallium Oxide Power Transistors. This is also my seed grant title. I received my doctorate degree under the SMART program. I was the 2014 cohort year. It was in electrical and computer engineering from George Mason University. I'm currently in phase 3 of the SMART program at the Air Force Research Laboratory Sensors Directorate, Wright-Patterson Air Force Base. So the slide said that they wanted us to give the director its overall mission, or our group's overall mission. So this is it here. Basically, it's ISR, combat identification, spectrum warfare effects. We do this for both radio frequency and electro-optical sensors. And basically, we're trying to give the United States an advantage over our adversaries. So below at the bottom there, the 4 pictures are 4 of our 6 core technical competencies. If you're in AFRL, you know what that means. If you're anywhere else, it's basically a binning of technical areas that we use, and they have a lead for each of those areas. So the 4 at the bottom here are RF sensing, EO and IR sensing, which are kind of the two main ones that are in the mission up there. Sensing autonomy, which is basically making the sensors work together, tipping and queuing, those types of things, and spectrum warfare, which is basically using the sensors in a warfare situation. The 2 others that are not shown here are foundational. One of them is mine, it's on the next slide. The other one is resilient electronics, basically taking all of these and making them so that adversaries can't affect our own electronic systems for sensing. So my core technical competency is the enabling sensor devices and components technical competency. We have in my branch, we have the electron devices branch, and we have 3 what we call level 2s, which is basically another bending. We have modeling and assessment, which is my level 2 that I run, device technology, and demonstrations and transitions. And then the graphic here at the bottom, maybe if I can find my mouse. The graphic at the bottom left is a layout of our CTC. You can see circled there is where I'm at, the electron devices group. We also have the other end of the electromagnetic spectrum, which is the EO and IR components. And then above that, we have highly integrated microsystems, which is basically like moving these toward an amplifier or towards some other application, some circuit application. And then even further above that, we have sensor subsystems, which are like multi-chip modules that would go directly into a sensor. So in the electron devices side of things, if you look over to the right side, it kind of shows the flow of what we do. So we look at the current and future RF environment, which is the picture, kind of the OV1 chart. So we look at the current and future RF environment, and then we say, what are the disadvantages that we have and what are advantages we can capture by using different materials or different material solutions. We get this information from DoD industry partners, from folks at AFRL and RX. We get it from academia, and we basically get this kind of spider chart that you see in the middle here that tells us, certain semiconductors can work differently than other semiconductors in certain areas. And so we go back to our RF environment and we say, well, how can we use that, the physics of those materials to exploit the RF environment for the United States advantage. And then our group specifically takes that information and tries to turn the physics and what we need in the RF environment into relevant devices. Usually those are transistors, like you see here in the bottom right. That's a SEM of a transistor gate and also a transistor itself. Usually they're transistors, but we do other things when needed. So to dig even deeper into the work that I do, so specifically right now, my group works on wide bandgap and ultra wide bandgap semiconductors. The reason that we want to do this is because those materials have higher critical field strength, which basically means that we can control the conduction up to a higher voltage. And then the critical field is basically when the voltage across the small channel, the electric field becomes too high, and this transistor will conduct without us controlling the conduction. So what is so good about that? Well, the critical field strength is directly related to two material figures of merit, we call them. And you can see the first one on the left side of the chart is the power switching. So your power loss of a switch is determined by that equation there. There's a conduction loss portion and a switching loss portion. So while you're conducting, it's losing basically it's a drop across the resistor. And when you switch the switch, you're also losing some power. So if you can look down to the boxes below that, you can see that the critical field strength that I just talked about for the high critical field strength for wide bandgap materials is in the denominator. So that basically means your switch loss is being reduced if you have a higher critical field strength material. So then in the plots at the bottom, you can see different materials, and you can see as you move to the bottom right of this chart, it is more advantageous for power loss. So you can see silicon, the dominant semiconductor, is not as good for this parameter, for this figure of merit, gallium arsenide. And then you get down to some of the better materials are gallium nitride, gallium oxide, and diamond. And the same thing on the chart next to it, you see the same thing, gallium nitride and gallium oxide are at the bottom of this chart. Moving to the right, the lower right is better. So those are the materials that we use. We focus on gallium nitride and gallium oxide in our group. We also partner with some of the folks that work with diamond over at Army Research Laboratory. And then on the right side of the chart is another figure of merit that's important for us. And this is the RF power figure of merit, known as Johnson's figure of merit. And it basically shows me that higher is better here, and we can get a higher Johnson's figure of merit if we have a higher critical field strength as well. So again, you see a plot. In this case, the better material is in the upper right corner. So again, silicon, not as good, gallium arsenide, and then you see gallium nitride and gallium oxide are quite good and comparable to diamond. So again, to reiterate, in the box below, we focus device research in gallium nitride and gallium oxide semiconductor devices because of this. Again, going back to the previous chart, we're basically trying to explore new areas of that RF environment to make advantages for the United States. So maybe this chart's a little, maybe too much detail, but this is more specifically what I do. So I work on, again, realizing the figures of merit in the device and the real devices themselves. So on the left side are some measurements that we've done on gallium nitride transistors, showing the high frequency operation. This is basically a cutoff frequency calculation with S parameters. And our bread and butter is the kind of lower left side graph here, which is a power sweep of the device. And it shows basically under real conditions what it can do in a power amplifier. So the output power, the efficiency, which is a very important parameter, it tells you how much power is being lost overall, and you can determine, heating, self-heating, and things like that from that number. So in the box over on the side, GaN, you can realize high gain at millimeter wave frequencies. It can also realize high output power at all frequencies with a good amount of gain. So that's why we look at gallium nitride. We call it GaN. I guess I just called it GaN. So hopefully people understood that transition. In the middle is a L-band low pull bench that the Smart Seed grant helped me refurnish, I guess, make better. It's still in work. I have a lot going on with it this year, and it hasn't all been smooth sailing, but most of it has been good. At least the Smart Seed Grant part has been good. And then on the right side, we have the gallium oxide. So the first measurement at the top is a breakdown measurement. So you can see gallium oxide has a very high breakdown voltage of 479 volts. And that's why we try to use it in the bottom. Again, this is a power sweep, but this is a different goal here. We're raising the voltage. The black curves you can see as we raise the voltage, the curves start getting higher and higher output power. And so that's what we're trying to do here. Gallium oxide is not quite as high frequency as GaN. So in the box, you can see gallium oxide. We're trying to realize high voltage at RF frequencies. So at, 1 gigahertz maybe, or some low frequency operation in the RF. And then we can get, if we can increase the gain, we can also use the gallium oxide for switch mode devices. SM is switch mode, which means that basically the device is switching on and off from an on state to an off state, and only has losses, much lower losses and much higher power added efficiency. So that's kind of what I do. I do a lot of this testing on the back end when the transistors are made, and we're trying to realize those goals from the material parameters. Okay, so a little progress on this. This is almost entirely related to the Smart Seed Grant. So a plug for the Smart Seed Grant if you have an opportunity to apply for it. So we're working with some partners to define better what the high voltage RF, or this is particularly for gallium oxide, can do for us. Some of those are the Army Research Laboratory, Texas at Dallas, and Oklahoma State University. Like I said, we're purchasing some gallium oxide material and some equipment for RF testing for gallium oxide from the Seed Grant. And then right now we're kind of in the troubleshooting stage. Like I said, things haven't always been going swimmingly lately, but we're basically trying to stand up an active low pull bench, which if you look at the lower left graph, gallium oxide is a very high output impedance. If it were in the center of the Smith chart, it would be very easy to match to, but since it's on the outside of this circle, it's basically very hard to match to. So active low pull can make it so that you can match the device out here. So that means you can get the maximum power delivered to the load. And so we're trying to make an active low pull bench for gallium oxide. And then on the other side, the graph is showing pulse low pull, what pulse low pull can do for us. So here we have different pulse lengths, and you can see the output power increases as we decrease the pulse length. So here we're trying to remove the thermal effects because we're basically testing on wafer devices, and they get hot. Gallium oxide doesn't have a very good thermal conductivity. So what we want to do is we want to see how well the device can perform without regard to the self-heating, and then eventually just engineer the self-heating out of the device. So this is very specific into the work of my Seed Grant, but also it's maybe too much or just enough detail on technical work that I've done. So with that, I'll go to the last thing, which is the SMART impact to me. So I'm a little bit different than maybe other folks have been, but SMART's benefits to me, the first one, well, I think that this may be for everybody. It helps you finish your degree. I might not have finished my doctorate if it weren't for SMART, certainly. There were definitely some trials and tribulations that went on there. For me, it helped me move back to the Department of Defense. I was actually an Air Force lieutenant. And so I needed to go back to DOD. At the time, I was in the intelligence community. And it also moved me back to Ohio. So I was able to get a sponsoring facility that was at Wright-Patterson. And it says in parentheses there, completed my research there too. So I did, like I said, it helped me finish my degree because I was able to do my research, hands-on research at Wright-Patterson. A lot of people talk about their interns. I basically never had an intern. I just moved here and then coordinated my degree back with George Mason University. So my internships were paper only, I guess. And then because of that, I was basically integrated directly into RYDD, the branch that I work in now after I finished my doctorate. So some of the things that have sort of been mentioned, but not really very straightforward, is other benefits of working in the DoD. So one thing is that I found is that you can do a lot of career broadening. And I think that Dr. Phipps kind of mentioned this on the previous thing, but I don't know if it's been mentioned by one of the technical briefs. So I work a lot with U.S. Space Force programs now because the sensors that we're developing have applicability there. And I don't think that you can really kind of do that kind of thing very easily if you're in another position. And there's a lot of other ways to do it. Like I said, I work with AFRL and those organizations as well. But this is maybe something that if you're at a PA designer, they want you to design PAs your whole career. And here it's actually encouraged to have career broadening. So it's better. It's better in that regard. So continuing education and training, a lot of people have said they went to some fun conferences or went on trips to see the things that they do. I would say that that you're also very encouraged to take courses even after your doctorate. So for folks that are just finishing their undergrad, you'll have plenty of opportunities to continue your education and training. And even if you finish your doctorate, you're still welcome to, like I said, I do things in the space arena. So taking orbital dynamics or something like that, they would encourage that type of thing. And I put it's a blessing and a curse there because we also have the mandatory acquisition trainings and those types of trainings everybody always wants to bark at. But those things can be good too. In my early career, I actually got a job because I had SFRDE level 2, and that's what they were looking for. So I worked for a contractor just because of that. And then last, I mentioned here funding and networking. You get to learn the research trade. When you're in academia, you kind of think you have to do this a little bit, but not quite as much. When you're in the DoD, you know how the money is handled because all of this stuff that we do is fun, but it also costs money along the way. So you get to learn that, and you get to be involved in it. Mentoring effects. By the way, my mentor is off to industry. He actually works for one of the contractors. So he did not, like a lot of people were talking about how they've continued their career in the DoD the entire time since they're smart. He did not, and he's very, very happy with what he's doing now. But there are opportunities to do that sort of thing as well. So they helped me align my research at George Mason with AFRL's goals and also with the goals of the Air Force at large. And then they showed me how to initiate projects, and that's how I was able to kind of do the Smart Seed Grant and execute the funding that I was giving and compete for those funds as well. And that's all I have. So thanks everyone. If there are any questions.
Thanks so much, Neil. Really interesting to see your progression from active duty and then wanting to come back and further your education and finding your way back to DoD. And then love the commitment moving on towards your facility to work with their facilities to complete that PhD. For those of you who are listening in and are thinking of applying to the SMART program, that's a really good way to align your PhD research with your sponsoring facility that selects you. It just really helps to solidify that, and really love to hear all the mentoring that you received at AFRL and where that's led you to today. Unfortunately, we have a couple of questions for you in the team chat, but we are going to have to move on to our next presenter. So feel free to respond to those questions in the chat there. Thank you again, Dr. Moser. Okay. And we're going to move on to Eric Sandel. Eric Sandel is with the Naval Air Warfare Center, Weapons Division, China Lake, and his project title is Solid Fuel Rotating Detonation Engine. Go ahead and share your screen. Great, you can see it.
Okay, and can you hear me okay?
Yes, we can.
Okay, excellent. Thank you everybody for listening to my talk. My name is Eric Sandel, and as Alexis just said, I am at the Naval Air Warfare Center Weapons Division at China Lake, called NAWCWD for short. I was able to get my master's degree in aerospace engineering at Georgia Tech in the 2017 cohort group. And so I am getting towards the final part of my phase 2 of the SMART program. I think that it is at the beginning of next year is when I'll transition over into phase 3. But just to get started, let's see here. Oh, there we go. Sorry, the screen wasn't going over. So just a brief introduction into what NAWCWD does. It is pretty much a one-stop shop for all weapons development for the Navy. There are 2 sister sites. China Lake, where I am at, is a huge land range in the desert of California. And then we have our sister site, Point Mugu, which is out on the coast for sea range testing and things of that nature. And, you know, everything from additive manufacturing, autonomy, to propulsion, energetics, software, networking capabilities. I mean, the list goes on and on about what goes on at NAWCWD, and it is a really exciting place to work. And I feel like I've been able to meet a lot of wonderful people that are doing amazing things. As far as what I do personally, I am a computational engineer in the Combustion Science and Propulsion Research branch. We pretty much do anything that is modeling of combustion or propulsion, typically high fidelity, you know, CFD or hydrocodes that we use to model these things. And a big focus is on solids in our group, but we're not necessarily restricted to that. And so some of the stuff that I have done, and here in this image on the bottom right, this is doing burn regression modeling for some solid fuel ramjet fuels. Here on the left is some aerodynamic heating for medium caliber ammunition. And then here in the middle, this is what I'm going to focus most of my talk today is on rotating detonation engines. So I actually didn't run these simulations, but this is just a good image to show what an RDE is. I'm not sure how many people are familiar with it. It's a little bit unique in the fact that it's not like a normal rocket where all of the combustion happens in a big cylinder. This one, the combustion is actually happening in this annulus on the side here. And you have a detonation wave that just propagates around this way while your thrust is getting produced by gases coming out your nozzle on this side here. And this has been a really exciting project for me, specifically with a solid fuel RDE, which is in very early stages of development and technology readiness. But this is where I've been able to do a lot of my work. And I know that I just said that I've been doing computational stuff, but I've actually been pretty lucky at China Lake to be a part of some of the experimental work as well. And I'll get into that a little bit. But basically, why are we even looking at a RDE and a solid fuel RDE specifically? So rotating detonation engines, they work on a different thermodynamic cycle than what many propulsion technologies do. So ramjets, turbo engines, things like that, they run on, they use what's considered called the Brayton cycle, which is basically a constant pressure combustion, whereas the RDE, which uses detonation, is similar to constant volume combustion, and it has a higher thermodynamic efficiency. So for the same amount of fuel and oxidizer, we can get better work output from it if we can, you know, control it and direct it properly. For solid fuel specifically, the Navy likes having solid propellants because they store better. It's dangerous and difficult to store liquids or supercooled gases on a ship. And so solids, they are typically safer and they can last longer as for the needs of the Navy. They also have a very high energy density. So you can get more energy out of a small amount of solid than you can out of the same volume in a liquid or a gas. And then with the RDE using a detonation cycle, the combustor size can be incredibly smaller. And so with that, you can cut back on weight of your combustor. So you can either put in more fuel, or you can put a bigger payload, or you can just make your missile smaller and increase your range, things of that nature. So there are a lot of positives to it if we can get it all to work correctly. And this work here is specifically on the fuel development for a solid fuel RDE. I guess to kind of get into the terms, I've been kind of throwing around propellant and fuel simultaneously. That's not necessarily true. For propellant, you have your fuel and your oxidizer together so that it's all in one spot. And so you can combust without having to bring in any external air or anything of that nature. Where a fuel is, just that, it's just the fuel. You have to bring in a outside oxidizer before it can react. And so technically with this gas generator, it is a propellant because it needs to burn on its own, but I'll often refer to it as a fuel because the products from this propellant then get mixed with air downstream to be the actual combustion mechanism in the RDE. So if you look at this cartoon here, this isn't an actual RDE. This is just a cartoon to kind of show it. But here in the blue, this would be your solid fuel that in the gas generator, which would then burn and gasify, and then it would come out here. And then on this port here, you would have air coming in. And so then it would mix and your detonation would come in this chamber here highlighted in the red, and it would come around. And then here in the brown, this is, potentially an idea for a booster. Since it's an air breather, you can't get thrust unless you have air coming in through the inlet. And so you have to get an initial velocity before you can take over into RDE. And so that's kind of a quick sum up of an RDE. But one of the big problems that needs to be addressed with a solid fuel is that we need it needs to generate a lot of combustible products. So when you're burning something, it tends to oxidize. And if you go back to your basic chemistry where you have, hydrogen and oxygen goes to H2O. Well, we don't want H2O coming off of our gas generator because then there's nothing to react with the air and burn in the RDE combustor. And so we need something that brings off a lot of fuel-rich products. But then the issue becomes, well, can you get your gas generator to sustain burning? When it's really fuel-rich, it's hard to burn. And so there's a big balance there on what formulations we need to be able to be effective in that, in this purpose. And so for this project, there is sorry, what do I have for time? A few different steps. I've been part of a really great team, quite a large team. And so I'm really grateful for everybody that's helped me out. But basically the first part is we had to get a model to predict how these different fuel formulations would perform. They are formulations that have never been used before. We don't have kinetics models for them. We don't know what reactions take place. So how can we predict, how it's going to perform without all that information? And so that was something that I started off with, was generating that model. But then from there, we formulate cast the propellants. We perform some experiments to get some basic information about it. Getting burn rates, gas chromatography and mass spectrometry. So actually, Dr. Patrick Fedek, who spoke yesterday, he actually is doing the GCMS for our propellants. And that basically gets us the equilibrium species experimentally, instead of just using theoretical calculations. And then, of course, and then we do actual detonation tube experiments where we are taking these fuels from the gas generator, we mix it with air in a long tube, and we try to detonate it and see if we can actually get a detonation to exist. And then going through and analyzing the data. I'll go through this really quickly. This is just the model that I created to predict the the gas generator performance. I used a equilibrium solver called PEP. It's similar to like NASA CEA, where you get equilibrium species based on combustion, but it doesn't account for any kinetics. So it's an ideal world where you have, infinite time to make all of the reactions occur and you get to a specific state. And I take those and I basically do linear interpolation at a bunch of different conditions, and I run that through a solver. And I am trying to predict, what the burn time for the gas generator is, what is the pressure inside the gas generator, whoops, that's right here, what our flow rates are, because this will all determine, the conditions that we're setting up for our tests. And as you can see over here on the side, the model actually worked pretty well. It fit the data, our experimental data, quite well. Not here for this one, but that's because the propellant burned really poorly. And there's some work that we have to do on the formulation side there. So now for the detonation tube tests, if you look here, this clearly does not look like a rotating detonation engine. So this is purely to get detonation properties of the fuel to see if it's even feasible for an RDE application. And so we've got the gas generator here. We burn it, we feed the gas down the line, we combine it with air here, and then we try to detonate it in this large tube. And then we have sensors going all the way down as we can track wave speeds and pressures. And in this first part of the tube, we have what's called a Shkelkin spiral. It's a tool to induce turbulence, which can then lead from a deflagration to a detonation transition. And so we're trying to accelerate the flame to get to a detonation condition. And as you can see here in some of our results, we actually never quite got there. And there are a number of issues that we ran into, but ignition delays of the solid propellant, timing, trying to get the high-speed data acquisition to occur at the same time as the wave as it propagates down the det tube. There are a variety of issues that we were working through, but we are getting really, really close. This is just one result here. And so the blue dots is the first tube right here, and then orange is further downstream in a slightly smaller diameter, and then the green is at the very end, just off of the picture. But you can see that our wave is still accelerating, and so it leads me to believe that we maybe aren't giving enough energy in our initiation to actually get a detonation. And so if we can just increase our igniter, then I think that we're going to be right there. I think we're really close. We are. This number here relates to just under the speed of sound. And for a detonation, we want to be going supersonic. And so we are really close to hitting over there. And we have some plans moving forward to get there. I won't talk too much about this, but it's just showing that we are actually capturing pressure gain, which is unique to the detonation cycle versus the Brighton cycle. So just to kind of sum up the RDE work, we still have a little ways to go, but I think that we're really close to getting a very cool and useful technology that will be very beneficial to the DoD. And as far as what SMART has done, SMART has been very crucial into my career. SMART allowed me to have a lot of flexibility in my schooling. And this was actually a wonderful thing. I was able to line up my internships at China Lake with my work that I was doing for my final master's project, which was cycle analysis for an RDE. And so it allowed me to be, directly involved in meaningful work from the very beginning. And it allowed me to gain connections and network with experts, even before I started my career full time. I was able to meet people that are, leading scientists and engineers in the RDE field. And it's been a wonderful blessing and a great way for me to be able to start. Specifically at China Lake, I've had some great mentors that have helped me to develop my expertise, that have given me opportunities to take classes, to learn more. And even, I've been there for less than 3 years, and I actually have my first proposals that I'm submitting as a principal investigator that are going in this Friday. And so I'm actually really excited about that. And I've had a lot of support from my supervisor to get me to that point. I've been able to be involved in other parts at China Lake as well, helping new scientists and engineers in the EPIC program, ES2P-NP Process Improvement Committee, to help other new hires to feel successful and to enjoy their career when they get started here. And then I love China Lake. I love being outside. It's kind of a secluded and isolated place, but if you're willing to get outside, it's a lot of fun. And so I've had a great time. So thank you everybody for listening. And if there's time, I'll open it up to questions.
Awesome. Thank you so much, Eric. Yeah. And congratulations on your next steps here. And great plug for China Lake too. I know it is an isolated area, but you've represented their work so well, and definitely your passion and enthusiasm is showing. There are a lot of questions for you in the chat. Unfortunately, we do have to move on to our final presenter, but I welcome you to answer those in the chat. There are quite a few rather technical ones as well. So thank you again, Eric, so much for your presentation and for joining us today. Okay. All right, folks, we're going to move on into our final technical talk for this morning's session. We have next Dr. Justin Clough with the Air Force Research Laboratory Aerospace High-Speed Systems Division, also at Wright-Patterson in Air Force Base in Ohio. And Dr. Clough's project title is High-Speed Vehicle Structures.
Thank you. And can everyone hear me okay and see my screen?
Yes, we can.
All right, excellent. Then let's get started. So yeah, I'll be talking about my work with high-speed vehicle structures. My name's Justin Clough. The SMART program paid partially for my master's degree and in full for my doctoral degree, which I received from the University of Southern California. And currently I'm working down at the Aerospace Systems Directorate here at Wright-Patterson Air Force Base in Dayton, Ohio. So our directorate mission, right over the door that I come in every day, is to boldly pioneering transformative space and air capabilities to make the fight unfair. And that that manifests itself in many different ways. These are just some select divisions and facilities that we have here at Wright-Patterson, and then spread throughout some of our sibling facilities throughout the country. What I'll be talking about today is where I'm working, the High-Speed Systems Division. So before we go any further, we should probably figure out what exactly high speed is and define that. So on paper, we draw the line that high speed is traveling at Mach 5, roughly 4,000 miles per hour, or any faster, generally up to Mach 25. Big numbers like that can be hard to grasp, so let's think of an example quick. Say you wanted to fly from New York to Los Angeles, that's roughly 2,500 miles. And if you did that commercially, that would take you about 6 hours as you travel at 80% the speed of sound. Traveling at Mach 5, you can cover that same ground in 45 minutes. And so I can't explicitly say in this space, but you can infer why the Department of Defense would like to be able to get up in someone's business in such a short amount of time. Our directors have a great history of these high-speed systems. It all began back in the 50s and 60s as we built the X-15. More recently, in the near history, is the X-51, one of the world's first air-breathing hypersonic vehicles. And then most recently, one of our current projects is the X-60 or X-60A. And within the world of hypersonics and high-speed vehicles, I'm working on the structure and keeping the wings on. One of the, as you might have assumed, you have many challenges that come into, that arise when you're traveling that fast. What people generally don't assume is actually it's the thermal part of the problem, all that air drag and air resistance they need to fight and overcome, and all that thermal energy that you need to deal with to keep things from melting or expanding or generally breaking on your structure. So let's think about for a second the SR-71 or NASA's YF-12A. If we look at this cross-section of the wing and its temperature distribution over a nominal flight, we can see that we start off with a thermal gradient of around 200 degrees per inch right here at the spar cap. And that's at our 8-minute mark, closer to 30 minutes as we're approaching our thermal steady state in the flight. We're around 400 and soon to be approaching 500 degrees Fahrenheit. And again, it's the fascinating problems that come with designing a material to be to survive both the cold environment, the hot environment, and that transition in between. We also have to consider those very high peak temperatures. So here on the right, I have a schematic of the X-15 again, along with some of the peak thermal loads that were observed during one of its test flights. So right at the nose, we have well over 1,000 degrees Fahrenheit. And then as we draw back towards the fuselage and towards the tail, we actually end up with the relatively cold zones of just down to 730 degrees Fahrenheit. And that 500 degree gap, more or less, is a very tough space to design in. And so I'm going to be talking about two specific projects that I've been working on, I guess, as I've joined the team here at WritePat. So first is the Automated Structural Layout Tool, or just AutoSaLT. And its purpose is to explore the structural design space for these conceptual high-speed aircraft. It's going to automatically perform a thermal mechanical analysis and post-process the results for the user. So one of the most tangible ways it does that is by considering as many geometric variants as the user requests. So a common workflow for us is that the aerospace and aerodynamicists will give us a vehicle OML that's just how it looks like from the outside, how big the wings are, how long is the whole vehicle, but they have no idea and no comment on what's going on inside, like how do you keep all that attached. So AutoSaLT is able to lay out different bulkheads, different ribs and spar configurations. From there, it's able to process a thermal solution as that vehicle travels throughout a nominal flight. And then it, again, post-processes those results to figure out, in this case, in this example, what is the driver as to what's causing the vehicle to be as heavy as it is. And so the whole purpose here is that you can add it earlier into the design loop. In the study that I'm citing down at the bottom here, we were able to run 96 different iterations of this vehicle in the span of about 6 hours. And that should be impressive because the old way of doing it, of having a structural expert sit down and click through each design, they would take 4 to 6 months to work through just one of those designs. And this is a product we are sharing. It's being currently shared with some academic and industry partners that I can't list out here at this time. As a separate project I'm working on is a thermal mechanical hybrid structures. And the goal here is that we want to passively manage those high peak temperatures and thermal gradients and smooth those out. And instead of using exotic materials, we're actually going to instead use readily available materials, namely metals, but we're going to be smart how we lay those metals out and build that geometry. So here I have, I guess, two panel joints. On the left is our baseline temperature, and on the right is the hybrid and, I guess, fixed joint temperature. I'm going to include a color bar here, so you'll just have to believe me that red is bad. And from that, we're able to reduce the failure rate of these joints from roughly 80% by the end of flight down into a more controllable range of 40% for some of our worst designs and 5% for one of our best designs. And so the whole the fruit of this project is that it produces these simple and lightweight thermomechanical solutions that can actually be quickly tested and fielded in our aircraft and vehicles. And this is also being a collaboration with the Department of Energy Labs for building and testing of these panels. And so I'll wrap things up, as I can already see I'm going over time, about how the being part of the SMART program and being a phase 1 and now 2 scholar has impacted me. Yes, the biggest thing that all the other scholars have mentioned is that there's no funding worries. And the cherry on top is that depending on the school you're at, you sometimes also receive some extra honors by holding this fellowship at the graduate level. Another thing is that the internships made it so much easier to collaborate with the scientists and engineers here at the base. As I received the SMART grant very early on in my, the SMART scholarship very early on in my graduate career, so I was able to align my thesis with the division's goals. And I was actually able to, when I was here interning, work on some of the more interesting side projects that the division had put together for me. The AutoSaLT tool I mentioned a few slides back actually started out as a project, I guess 5 years ago now, during my first internship here at the base. Additionally, they asked me to write down some cool things that I've done. There's a very long list, but I wanted to include my top 2. I received this is about a year ago now, I received a personal tour through the United States Air Force Museum by the chief engineer who had designed at least one component on what seemed like every plane in there, especially the X-15, which is just down the street from me as I speak. And then second, and I can only say so much about this, I've had a very unique experience to have hands-on time with some of the X-plane hardware, both historical and more current vehicles. And then the last thing I'd like to mention is that even though I'm only 1 year into my career, or 11 months to be exact, I feel like I'm coming in with 4 years experience. I already know everyone on my team. I know all the people I need to email when problems come up. I know my path forward. It's a lot better than coming in the middle of a pandemic and treading water and hoping for the best. So that's all I had prepared. Thank you for listening.
Thank you so much, Dr. Clough. Wonderful presentations this afternoon. We heard a lot from AFRL out at Wright-Patterson. So we've got a lot of folks that are doing wonderful work, and we're so honored to be able to highlight that work here at our symposium. So I'm very grateful to all of our speakers this morning. Hopefully everyone sticks around for our afternoon session. Again, just some programming notes as we go into our break. The link will stay on Active Live. It'll be the same link for this afternoon's session. So we hope that you do come back for this afternoon's technical talks on artificial intelligence, autonomy, and advanced software and computing. That will begin promptly at 12:30. So thank you again to all of our speakers from this morning's session, and we look forward to seeing you all at 12:30 after our brief break. Thank you.